Jnanam Paramam Dheyam. Knowledge is supreme.
All right. So, in few minutes back, we saw ring homomorphisms, algebra homomorphisms, examples, and so on. Now, let us continue a little bit more. In group theory, one studies now how do you get an isomorphism from a given group homomorphisms, or how do you test a given group homomorphism is injective or surjective, and such corresponding things for the ring homomorphisms or K-algebra homomorphisms. I am going to state only, and the proofs I will leave it to the participants. They are exactly along the same lines as one do in a group theory. So, for example, so when do we say that, how do you test that given ring homomorphism R2S, ring homomorphism phi, injective, so phi is injective if and only if the kernel phi, which is by definition all those elements of the ring R which are mapped to 0, that is phi of x is 0. So, this is a subset of R, and it's not just a subset, it has some more properties. I will come in a minute. So, phi is injective if only if kernel of phi is consists of 0 element. There is no non-zero element of R goes to 0 under phi, then phi is injective. Now, what are the more property? What are the more property of this kernel? That it is an ideal. Kernel phi is an ideal in R. So now I have used this word, new word, ideal in R. So that simply means, that is, first of all, under addition it is a subgroup. So kernel phi under addition is a subgroup of R plus, that is one. And another property is, if I have arbitrary element A in the ring R and X in the kernel, then A times X is also in the kernel. And because we are in a commutative ring, we are not going to bother about left ideal, right ideal, and so on. Similarly, here you only it's enough that we multiply on the left. So it is better that we assume now rings are commutative always. Okay, that is an ideal. I will soon give examples of ideals in some rings. Like injectivity, how do you test the surjectivity is easy. That as usual for map between the two sets, we denote image of phi to be all those elements phi x as x varies in R. Take all the elements of R and take all their images. This is a subset of S which is called the image of S. And note that this is a subring of S. So let me remind you, subring means with respect to the same binary operations plus and multiplication of S, this subset induce on this subset is also a ring. And in particular that 1 also belongs here. So for that, let me remind you, because our assumption is very important, 1R goes to 1S. So that means 1S is in the image. So 1S belongs here. And the remaining properties are just follow from the fact that it is a ring homomorphism. So if you if you want to, and what is an isomorphism of the rings? Isomorphism of the rings that means a ring homomorphism which is bijective. This is equivalent to saying that phi, so isomorphism phi from R to S is a ring homomorphism which is bijective. That means phi and phi inverse both are ring homomorphisms. Remember, because of this bijectivity, phi inverse makes sense. And both are ring homomorphism, then one says it is an isomorphism. And this is usually denoted by R to S phi, and to show that it is bijective, it is denoted like this. So this is a typical notation one will use for isomorphism of rings. And for injectivity, normally one writes R hook arrow S. So this means injective. And R to S, surjectivity is denoted by putting two arrows. This is surjective. This is the standard notation we will adopt in this course. So now let us see some examples of rings, ideals, isomorphisms and so on. So first of all, I want to give some examples where we can describe the ideals. So first, one can describe all ideals in Z. So how do you do that? So take the ideals, they are usually denoted by the Gothic letters A, B, C, etc. These are introduced by Dedekind. Dedekind was a German mathematician, and therefore he used German letters which are Gothic letters to denote ideals in the rings. So suppose A is an ideal in Z. Then I want to show that it is generated by a single element. What does that mean? First of all, before I started this, I should have given examples in arbitrary ring. So let us take R be any ring and X be any element in R. Then if I take all multiples of this X, R multiples of X, that obviously I will denote by R times X. This is by definition all A times X where A is varying in R. And I want to check that this is an ideal in R. And how do I check that? So I have to check that it is an subgroup under addition, which is clear, because if I take two elements like this Ax plus Bx, then because of our rules, this is nothing but A plus B when I add first and then multiply. So therefore it is again a multiple of X, so it is closed under addition. Similarly, it is closed under negation, because minus of Ax is same as minus A into X. So it is a subgroup, and it is clearly closed under the scalar multiplication of R, because if I take C times Ax, which is same as Ca times X. So what we have checked is this is an ideal in R. This ideal is called the principal ideal generated by X. Principal ideal generated by X. And note that this X may not be uniquely determined by this ideal. If you give the ideal, then you need not get back X. For example, minus X will also generate the same ideal. So R X is same as R minus X. Remember, this means all are multiples of minus x. Minus x is a additive inverse of x. So these two ideals are same. So therefore, in particular, not only this, in particular also this is also same as r times r multiples of any ux, where u is a unit in R. Remember, we had this notation for units in R. These are the set of all invertible elements with respect to multiplication. So these two ideals are, so u and x and ux generate the same ideal. So you cannot recover a generator from an ideal. But if it is generated by a single element, then one calls it a principal ideal generated by x. And the first statement I wanted to make, that all ideals in Z are principal. So we have a good knowledge of ideals in the ring Z. And how do you check this? The important tool to check this is what we have mentioned earlier, the division with remainder. So to prove it is principal, we may assume A is 0, non-zero, because if A is a 0, 0 is always an ideal in a ring and it is clearly generated by 0. So it's principal. So similarly, I can also assume A is not R, because R is also an ideal, R is generated by the element 1. So these are called trivial ideals. Trivial ideals is 0 and the whole ring. They are obviously ideals in any ring. They are called trivial ideals. R is usually called a unit ideal and 0 is called a zero ideal. So to prove it is principal, I will assume A is non-zero and A is also R. If any one of the case happens, then there is nothing to prove. Now we have a proper subset of Z, and I look now, I take the minimum element. So let us take A intersection N. I claim this is non-empty, because I know that A has at least one non-zero element. If it is positive, already that element is in N and A, therefore it is non-empty. If that element is negative, then I take negative of that element which is also in A, because A is an ideal, and therefore in any case A intersection N is empty. And now I want to use the basic property of natural numbers, which says that every non-empty subset of natural numbers has the minimum. This is called well-ordering property of N. That says that every non-empty subset of N has a minimum. So I apply to this subset. So choose N in A intersection N, which is the minimum of A intersection N. And claim is A is nothing but all Z multiples of N. That is what we want to prove. And that will finish our proof that A is a principal ideal. So obviously this inclusion is obvious, because we chose this N to be in the ideal A. So because it is an ideal, all Z multiples of N are also in that set, because it's an ideal. The second condition of the ideal, that if I take arbitrary element in the ring and arbitrary element in the ideal, then the multiplication is also again in the ideal. So this is clear. I want to prove the other way. So start with any element A in A, and I want to show that this A is a multiple of this N, Z multiple of N. So what can we do with A and N? A and this N we have given. Obviously this N is non-zero, because A intersection N, we are assuming we have chosen a non-zero element in A intersection N. So this is the minimum. and now we can divide A by n. So therefore write, by division algorithm, write A as q times n plus a remainder r, where q and r are elements in Z and r is strictly less than n. Now look here, this equation says that this A is in A, this n is in, this multiple is in Z multiple, therefore it is in the ideal A. So when I shift it to this side, A times Qn, this is R, but this is in the ideal A because of the definition of the ideal, and therefore R has to be 0. If R is not 0, that will contradict the minimality of n. So just to be very sure that we have taken, remember we have chosen n in this, which is the minimum of this minus 0, I should have said. That is why we need to assume A is non-zero. So therefore this proves that all ideals in Z are principal, and remember the only tool we have used in this is the division with remainder. And not only that, if I choose now, what are the choices, how many can I recover back from this ideal, this n, a generator? There are only two possibilities, because we have in this ring has a property that the units are only 1 and minus 1. These are the only two units. So therefore, the only possibility is the Z multiples of n is same as Z multiples of minus n. So therefore, this ideal A is generated by a unique, I will now say a unique natural number n. Unique natural number n, because this gives a possibility to remove the negative ones. So, and nothing special about this ring. So I will state without proof, and one should check this. I will just say similarly, check that in the polynomial ring, Kx, where K is a field, every ideal A is generated by a unique monic polynomial fx in Kx. Same proof. We just take, because there we have used the division algorithm. Here also division algorithm is available because K is a field. Okay. So before I go on, at least one example where not all ideals in all rings are principal. For example, in the ring Z, polynomial rings with coefficients in the ring Z, the ideal, so ideal A, which is generated by 2 and x. What does this mean? This is indeed an ideal, and also check that this ideal is not principal. This I will leave it for you to check. Okay, so on the way we are going to find more examples of ideals, right? So I want to give few more examples of algebra homomorphism. So for example, examples of K algebra homomorphisms. So we have two K algebras. So one K algebra, so K is a field I will take, though it is not really necessary that K is a field. But if I keep assuming more general thing, then this course will get more and more delayed and more going away from our aim. So let us assume that K is a field, and the typical K algebras we are going to deal is Kx, a polynomial ring over K in one variable x. So this is clearly a K algebra. So typically you should keep in mind, take K equal to Q, and these are all polynomial with rational coefficients, or K equal to R, or K equal to C. These are the typical examples. And we now take K itself is a K algebra. K is also K algebra with the same scalar multiplication as a multiplication in K. So I have these two K algebras, Kx and K, and I want to give a map between these two, which should be K algebra homomorphism. And K algebra homomorphism means it's a ring homomorphism and it is K linear map. So given any element A in K, this epsilon A or EA, E is for evaluation. Evaluation at A. What is this map? Take any polynomial f and map it to f of A. F of A is A times A0 plus A times A1 plus so on. Just put wherever there is x, put that is A. And the next term will be, I should actually write the coefficient first. So A2 times A square, etc., An times A power n. This makes sense in K now, because all these are elements of the K. That is precisely why we needed a concept of K algebra. So this is precisely what we call it f of A. And we are interested in, given an element, given a polynomial f, we want to find A so that f of A is 0. So that means precisely we are interested in finding out the kernel of y. This is what we are interested in. And particularly knowing whether it is, so it's an ideal. We know kernel is an ideal. This is a ring homomorphism, therefore this is an ideal. And also we know it is a principal ideal. Also we know that this ideal is generated by a unique generator, unique monic generator. And that is what we are going to formalize further and in a little bit more general situation. But before I do that, I also need a construction of a new ring by using ideal. So remember, from Z and given any integer n, natural number, we have constructed a new ring called Z modulo n. This ring was constructed by using Z and n by taking the operations addition modulo n and multiplication modulo n. Similarly, given any ring R and given any ideal A, I am going to construct a new ring which will be denoted by R modulo A. So the new ring, the addition there, I will use a similar construction. That means I will introduce an equivalence relation which will be defined by A and take the equivalence classes, and on the equivalence classes I define addition and multiplication. And how do I do that? It's very simple. Take any x define an equivalence relation by x, y in R, then we say that this is a definition. X is related to y under A should come somewhere notation. So I will just write simply this. So this means x minus y should belong to the ideal A. And now we will I will just say that check that this is an equivalence relation on R, and let us denote the equivalence classes X suffix A here, equivalence classes, class of X. And obviously how to add is add as usual and take its equivalence class under A, and then you check that these operations are well defined and the same, everything is same. If one gets stuck, go back to study this example. So from this ring R, we have this new ring. So R we have passed on to this new ring R by A, and also we have a natural map here. This is I will denote by pi A. This is X going to equivalence class of X under A. And also I will leave it for you to check that this is a ring homomorphism. Ring homomorphism with kernel the given ideal A and image of pi A is the whole R by A. That means this, in other words, this pi A is the canonical surjective ring homomorphism from R onto R by A. So that is the kernel. Now we are in a much better position to describe what algebraic element means and what algebraic extensions are, but this program I am going to carry out in the next lecture. And just to summarize, what we have seen in today's lecture is rings, ring homomorphisms, algebra homomorphisms, kernels, image, and so on. And now we will, in the next lecture, we will introduce the concept of algebraic elements. We will introduce the concept of field extensions which are algebraic, and also define transcendental elements and so on, and use this further to one of our main step, the beginning step, that given a polynomial over arbitrary field, we extend the field in such a way that all the zeros of this polynomial lie in the bigger field. And this we do it for single polynomial first, and then we do it for many polynomials, and as a consequence we will deduce the fundamental theorem of algebra, namely that is the field C is algebraically closed. With this I will stop today. Thank you.